Okay, welcome back to CMOS RF integrated circuits. We are lecture 10, part of module 3. We were discussing passive components, and part of that we were discussing wires. So far we have already covered inductors, capacitors, resistors, all of this stuff we have already covered. We were discussing wires, and as our discussion about wires, we were first talking about the skin depth, skin effect and skin depth, which we have mentioned before. So, if I have a wire and current is traveling through the wire at a frequency, at an angular frequency of omega, then the depth up to which the current is going to travel, actually my statement is not really true, but that is how I am going to phrase it. To an engineer, the depth up to which the current is going to travel, that is d, is given by this formulation square root of 2 by mu sigma omega. So, as omega increases, this depth decreases. Okay. Why I said that this is an engineer speaking and not a physicist is because if you look at the real derivation, then at this depth the current density is about 1/3 or rather 1 by E times the current density on the surface. That is what it really means, but to an engineer this is the depth at to which you can assume that current is going to travel. Okay. After this we were basically we had started looking at the effective inductance per unit length of a wire. Now, why we are saying per unit length is going to become apparent to you in a short while, but for now let us just try to figure out what is the inductance. So, we have a wire which is carrying I and there is a return path for the current. So, there is another wire which is coming back, it is parallel to the original wire. This is the case situation that we are going to talk about, and why we are talking about this as a special situation is because when I have a wire over a conducting ground plane, then an image of the wire is going to be beneath the ground plane. So, this situation is routinely going to arise in our integrated circuit. So, that is why we are specially talking about this situation. Now, we are going to assume that this wire has a circular cross section. Unfortunately, on an integrated circuit the wires do not have a circular cross section, they are going to have a rectangular cross section, but this is an assumption because if I do a rectangular cross section the derivation is going to become unnecessarily complicated and I would rather not do that derivation. So, this is what I am going to do. Now, at a distance x from a current I, so I have a uniform current going through a wire, current is I of t. So, at a distance x from this current, how do I measure the magnetic field? How do I find out the magnetic field? I create an Amperian loop at a radius x around the wire. So, presumably the integral of the magnetic field along this loop is going to be I am sorry, the magnetic field along this loop is going to be a constant. So, the integral of the magnetic field is going to be magnetic field times 2 pi x. Now, this quantity is mu naught times I, that is Ampere's law. So, that quickly gives us a result that magnetic field because of this forward current I at a distance x is mu naught I by 2 pi x. Now, this is not telling me anything about the return current. Return current we are going to do it later. So, I am going to assume that the return current is going to add some more magnetic field to the original, right. So, if this is x and let us say this is y then the return current is going to create another portion, right. So, this is superposition. I have just used superposition over here, and this is correct. This is going to be the field. So, in any case, I am not going to consider the return current right now, we are going to think about it a little later. Why a little later is because let me think about the flux because of this magnetic field. So, let me try to compute the flux over this entire hatched area with red, that red marked portion. Let me try to compute the flux through that area. Now, the length of this is L, okay, and let us say the bottom wire is at a distance, what do you want to say, h from the top wire. So, the gap between the bottom and the top wire is h meters. Okay. So, the flux is going to be the magnetic field integrated over the entire area. Okay. So, I am assuming that this wire has a radius of small r. So, let us look at the area from r to h, r to r plus h, I am sorry. Let us say this is h. So, this gives me this integral results in log. The integral of 1 by x is ln of x. So, basically what I get is something like this. So, this is the total flux because of the top current, the forward current. Now, if I look at the return current is also going to give me a similar integral, and the result is basically going to be identical. So, the forward current is going to create some flux, the return current is also going to create an identical flux. So, total flux is going to be twice of this. So, that is mu naught I right, and d phi by dt, the rate of change of flux creates an EMF, which is the. So, if I try to change the flux, then an EMF is created which is equal to the rate of change of flux, rather a back EMF is created. It resists the rate of change of flux, which basically means that I get a potential drop across this wire, which is equal to d phi by dt, and that is going to be equal to mu naught L ln h by r by pi times d I by dt. Now, if I have an inductor of value L, then the potential drop across the inductor is L times d I by dt, and here I have got something across which there is a potential drop which is some constant times d I by dt. So, the inductance of this piece of wire is this. And if I want to consider inductance per unit length, then it is the total inductance divided by the length. Okay. So, there have been a lot of simplifying assumptions in this derivation. However, what I need you to understand from this is that even a wire has some inductance per unit length. Longer the wire, more the inductance, right. Also, more the separation between the wire and its return path, more the inductance. Okay. So, things will change if you change the geometry. So, if instead of a circular cross section you go for a rectangular cross section, things will change. As an engineer, I do not really care about these small changes. I need some intuitive understanding of what is going on, and this result gives me an intuitive understanding. That is good enough. Okay. Oh, one more thing, as you make your wire thinner and thinner, the inductance per unit length becomes more. So, thinner wires have more inductance, thicker wires have less inductance. Interesting. All right. So, a wire has inductance per unit length. Does the wire have resistance per unit length? Yes, we already discussed that. We even discussed the cross section and the skin effect and so on, how the resistance is not really a pure resistance, it keeps going up as a function of frequency, etc. What else could a wire have? Maybe it has capacitance. So, let us consider our wire. Okay, now for convenience, I am not going to use a circular cross section, I am going to use a rectangular cross section. So, whenever whatever is convenient, I am going to do that, right. So, let us say I have a wire carrying a current I of t, and of course, if you have a current going, the current has to come back, and there is a return path of the wire, which is basically the mirror image of the wire on the ground plane. Something like this. Now, this reminds you of parallel pair of plates, right. The more the separation, the more the fringing, but even otherwise this is a parallel plate capacitor. And if you just think about a parallel plate capacitor, the capacitance between the two plates is going to be equal to the area of the plate times the epsilon of the dielectric material divided by the gap between the two. We said the gap, let us say, is h, right. This is what it is. What is the area of the plate? Area of the plate is the length times the width. This is not taking into account the fringing. Fringing is only going to add to this further. and what is the fringing going to be proportional to? The fringing is going to be proportional to the perimeter of the plate. So, it is going to be proportional to the perimeter of the plate, and it is also going to be proportional to the height of the plate. I hope you remember this. I mean, just look back a little bit and you will recall that the fringing capacitance is proportional to the perimeter, which is L plus W, and it is also proportional to the height. I am sorry, not that height, the thickness. So, let us say the thickness is also W. Let us say the thickness is also W, and it is inversely proportional to the distance between the two. It is also proportional to the dielectric constant, and then we said that there is some fudge factor, something, some number over there which we do not know, which we need some computational expert to figure out what it is. Fine. All I want is some understanding, some feel for what is going on over here. Now, L plus W can be approximated as L, right? W is small, L is large. Okay. This W is really the thickness of the plate, but if you consider that earlier we were talking about a circular wire which has both dimensions equal, radius is r, means the height is, the thickness is the same as the width. So, that is why even though we are going for a rectangular cross section, let me just assume that the thickness is W and the width is W. So, I just want to try to mimic the earlier computation, that is why, no other reason I chose that to be W. Okay. So, this is my capacitance, and the capacitance per unit length is basically W times epsilon by h divided by 1 plus 1 by this fudge factor. Right? What does this tell me? So, look at the conclusions earlier and look at the conclusions now. The earlier conclusions were, when we were doing inductance, the separation between the two wires increases, inductance increases. The radius of the wire decreases, inductance increases. What are the conclusions now? The separation, if I increase the separation, the capacitance per unit length decreases. If I decrease the radius of the wire, my inductance increased. Where was that? Yes, inductance increased when I decrease the radius of the wire. If I decrease the width, width is comparable to radius because we chose a square cross section. So, if I decrease the width, capacitance is going to, capacitance per unit length is also going to decrease. So, just the opposite effect as before, right, precisely the opposite effect. So, when inductance increases, capacitance decreases, when inductance decreases, capacitance increases. All right. So far, so good. If I had chosen the same geometry for both, as in if I had chosen both circular or both rectangular, which I did not, because I wanted to simplify my computations. But if I had chosen both geometries as the same, then you would find that L prime inductance per unit length times capacitance per unit length would be a constant. Okay. Unfortunately, I can't prove this because we did it differently. No. When inductance decreases, capacitance increases. When inductance increases, capacitance decreases. So, it kind of gives you a sense feeling that L times C is probably going to be a constant. It so happens that it is a constant. For a given geometry, it is constant. You have to do the correct computations for both, you will come up with this result. Okay. So far so good. So, we have figured out that when I say that I have got a wire is really something else. It is not a short circuit, it has some inductance per unit length, it has some capacitance per unit length, it has some resistance per unit length. If the dielectric material is no good, suppose the dielectric material was conductive a little bit, then there would be current also leaking out over here. If the dielectric material was not a perfect insulator, then there would be current leaking out, and that would create a conductance per unit length as well, right. So, our model for the wire looks like this. Okay, I am not being very proficient with this. Okay, so let us so this is a little bit of a section of a wire. Okay. Let us say I have got a wire of very small length d l, then this is the model for the wire, and a wire of huge length is basically a cascade of these sections till I complete the entire length of the wire, right. So, this is my model for a wire. It is a cascade of a lot of these sections. Each section has its own inductance, resistance, capacitance and conductance. Okay. It so turns out that the conductance is mostly going to be equal to 0. For most dielectrics, reasonable dielectrics, this conductance is going to be equal to 0, unless you choose a bad dielectric material, you should not be having a conductance. For example, on an integrated circuit, the dielectric material is silicon dioxide, it is more or less a perfect insulator. So, you can safely assume that G prime is 0, boom. So, one simplification at least, G prime is 0, right. But we still have to live with inductance per unit length, resistance per unit length, capacitance per unit length. This kind of a system is called a distributed system. The inductance is distributed. So, a wire has certain inductance, but this inductance is distributed all over the wire. It also has distributed resistance. It also has distributed capacitance, right. If the capacitance were not there, then I could lump both the inductance and the resistance, because all of these come in series and they add up nicely. But because there is the capacitance, you can't do that. Okay. So, how do we analyze a distributed system? Let us say that I have applied a voltage V this is my x axis. Okay. At a distance x, the voltage that is on that piece of wire is V, and at a distance x plus, let us call this dx for convenience instead of dl. So, at a distance x plus dx, I have got a voltage V of x plus dx. Also, let us assume that the current going in is I of x over here, and the current coming out is I of x plus dx. Okay. Now, these quantities are almost equal, but let us develop some kind of an equation relating them. So, the first thing that you see is V of x plus dx is equal to V of x minus I of x times L prime dx minus I of x times R prime dx. This is the first important thing to observe. And the second important thing to observe is I of x plus dx is equal to V of x plus dx minus, so some portion of the current is I of x minus, oh, I made serious mistakes. So, the current through the capacitor is C dV by dt. So, that much current is leaking out through this capacitor. So, the current that is going out of the network is I x plus d x, that is equal to I x minus whatever is the current through the capacitor. That is my equation number 2. And equation number 1 is the voltage drop. So, I have applied a voltage V x at the input side, and on the output side it is V of x minus the drop across the inductor, that is L d I by dt, minus the drop across the resistor, that is resistance times the current. So, that is what I have got. Now, if you look at these two equations, they are partial. So, really V and I have to be functions of x as well as time, because you are doing derivatives with respect to time. So, all of these derivatives are going to become partial derivatives. So, you have now got a pair of partial differential equations in two variables x and t. And let us simplify a little bit. Let us bring all the voltages together. So, I have got V of x plus d x minus V of x is equal to this, and let us divide the left hand side by d x. So, I divide the right hand side by d x as well, and what I have got is so this is what I have got from equation 1. And if I rewrite equation 2, similarly, I am going to get dou I of x t by dou x, and that is going to be equal to minus dou v of x t by dou t times c prime. So, these are going to be the pair of partial differential equations that we have to worry about. There would have been a fourth term over here, which would look very similar. But of course, I am assuming g prime is 0, does not matter, you can let it be there in the set of equations. Okay. So, now that we have this, does this remind you of anything? This pair of equations, does it remind you of anything? May or may not remind you of anything. Let us first look at how can we simplify it further. It should remind you of Maxwell's equations, but anyway, let us first try to simplify this further. So, what I am going to do is I am going to take a further second derivative. I am going to do a further differentiation of equation number 1 with respect to x, and that will give me dou squared v by dou x squared on the right hand side, on the left hand side, and on the right hand side I am going to get dou squared I by dou x dou t times L prime minus dou I by dou x times r prime. And I am going to do another differentiation of equation number 2 with respect to t. If I do a differentiation of equation number 2 with respect to t, I get dou squared I by dou x dou t is equal to minus dou squared v dou t squared c prime minus dou v dou t g prime. Okay. Now, we are going to plug in the value of dou squared I by dou x dou t. So, let us call this equation 3 and 4. 4 gives me a relationship of dou squared I dou x dou t purely in terms of voltages. Okay. Equation 2 gives me dou I by dou x purely in terms of voltages, and equation 3 is something which is mixed up. So, I am going to replace each term in equation 3 and make everything purely in terms of voltages. So, what I am going to get is something like this. So, this is my final differential equation. It is all in terms of voltages and only voltages, but there are two variables x and t, right. So, voltage as a function of x and time, distance and time, and the entire equation is only in terms of voltages. Similarly, I can work out something for currents, and what you are going to get is something like this. Just going to write it out. Okay, all in terms of currents. Okay. So, we now have one equation for voltage as a function of x and time, one equation for current as a function of x and time. Of course, the voltage and the current are also related to each other. You have to keep that in your mind, at the back of your mind, but that we will use as a fact later on. But all the voltages are in one equation, all the currents are in one equation. Now, do these equations remind you of anything? So, let us say, to start with, let us say that this resistance per unit length and the conductance per unit length are both equal to 0. Let us simplify matters and say that R prime and G prime are both equal to 0. So, when R prime and G prime are both equal to 0, then this term is missing, this term is missing, of course, these two terms are also missing. Now, does this equation remind you of anything? Both the equations are actually the same. Do these equations remind you of anything? Yes, they should remind you of the wave equation. If you go back to your engineering mathematics, or I do not know what book you have studied before, both of these equations are basically the wave equation. They are out of a textbook, and the theory of differential equations say that if you know the solution to a differential equation, then that is the solution, right. So, the solution to the wave equation is basically as follows. There is, so V of x t is going to be a function, let us call it V plus. This is a function okay. Oh, I am sorry, I won't write it as V, I will write it as C, where C is equal to 1 by square root of L prime C prime. Okay. So, C is kind of similar to the speed of light, it is basically the speed of the wave propagating over the wire. So, if you do your computations correctly, then L prime and C prime should give you the speed of the wave, and the speed of the wave is going to be very related to the speed of light. Typically, this is what you are going to get as the speed of the wave. Okay, which kind of tells you that if you happen to know the inductance per unit length, you can easily compute the capacitance per unit length without doing detailed derivations. But anyway, we did two different geometries, and then we got then we did some hand waving, and then we said that really they are going to be, things are going to be identically, the product of L and C is going to be a constant, etc. We just hand waved our way through. Anyway, so this is actually the reason why the product is going to be a constant. It is the speed of light on that particular material. So, there is a lot of physics behind it. We just hand waved our way, and we said one is an inductance per unit length, one is a capacitance per unit length. Really what is happening is that an electromagnetic wave is propagating over the piece of wire, and the speed of that wave is a known quantity. The speed of that wave is 1 by square root of mu times epsilon. Okay. All of these are actually coming from Maxwell's equations, and we are reformulating Maxwell in our own convenient way in terms of voltages and currents. Maxwell wrote his equations in terms of electric and magnetic fields, right. The electric field, integral of the electric field is going to give you the voltage. What about magnetic field? How does it relate to the current? A current is going to give you a magnetic field at a distance. So, they are kind of related to each other. However, we have spun it in our own way. Okay. So, this is the solution to the wave equation. V plus indicates a forward moving wave, V minus indicates a backward moving wave. These waves are moving at a velocity c meters per second. Similarly, I of x t is also going to give you very similar solution. Okay. Now, this V plus and this V minus, these are functions of x and t, and that is really the relationship of how it is a function of x and t. It is really a function of x minus c t, function of x plus c t. Okay. That is what it means. All right. You can plug these back into the original equations and you will get your desired results. You will see that they work. Okay. Our equations are somewhat different. We assumed over here that G prime and R prime are 0, right. G prime and R prime create a loss in the wire. When the wire is completely lossless, an electromagnetic wave can propagate over the wire without any attenuation. If the wire is lossy, then the electromagnetic wave is going to get attenuated as it propagates over the wire. Okay. So, all this velocity etcetera, they are going to be fudged up once we plug in non-zero conductance and resistance per unit length. Okay. Hopefully, the conductance per unit length is anyway equal to 0. So, for silicon G prime is 0. Okay. So, how are you going to solve this? Now, I already gave you a hint with the electromagnetic wave. When I talk about electromagnetic waves, they are typically sinusoids or a sum of sinusoids, right. It is easy to think about sinusoidal waves. Any waveform, any shape, complicated shape, let us say a pulse or a square or whatever you want, can be dismantled into a lot of sinusoids at a lot of different frequencies. It is possible. Now, I am going to use that fact and I am going to assume that maybe a sinusoid is going to fit my bill. Let us see if it does. So, now we are going to start talking about phasors. So, let us say V is the phasor, capital V is the phasor for voltage, capital I is the phasor for current. Okay. So, these two equations are going to be modified as d squared V by dx squared, that is equation number 1 is equal to L prime C prime. What is the second derivative of the phasor of the phasor V? What is the second derivative? So, if I have got V cos omega t, or let us say I have got V times e power j omega t, then the second derivative is going to give me omega squared times the original. Is it omega squared or minus omega squared? Minus omega squared. So, cosine to sine and then sine to cosine again. So, that is one negative, or you can think of j omega times j omega is minus omega squared. And the second term will give you. So, what is the first derivative of the phasor V? It is j omega times V. And the third term is V times G prime. Okay. And similarly, you can work out the equation for the current. It is going to be a very similar equation. So, let me rewrite this equation. Similarly, the current equation is, I am just going to replace all the inductances by capacitances, all the resistances by conductances and vice versa. Right? We have got two beautiful equations. What is the solution? What is the solution to this? Dou squared V by dou x squared is something times V. So, what should V look like? V should look like an exponential, right. I do not know what this k is, and you plug it back in, V equal to e power k x. So, dou squared V by dou x squared is going to be k squared times V, and that is whatever is inside the brackets times V. So, really k should be equal to the square root of the quantity inside. Now, the square root of the quantity inside, it could be the positive square root, it could be the negative square root. You always have two square roots. First of all, it is a complex quantity, there is j omega times something, right. If the resistance was 0, if the conductance was 0, then it would not have been complex, it would have been purely real, it would have been a negative quantity in fact, real and negative. So, the square root of a real and negative number is plus or minus j times something, right. Square root of a complex quantity is going to be what? Square root of the magnitude times exponential of plus or minus j times the phase, right. So, we need to understand that there are two solutions for k, one is the positive root, the other is the negative root, right. So, what is the voltage finally going to be equal to? Finally, the voltage is going to be equal to e power the positive square root of this thing times x plus e power the negative square root of whatever is in the bracket times x. Okay. And this positive and the negative square roots, these are both complex numbers. Agreed? Okay. So, these are both complex numbers, means there is going to be a real part to it, there is going to be an imaginary part to it. So, the positive and the negative square roots, let us say these are sigma plus minus j omega. Okay. So, I have got okay. So, these two are basically going to give me a forward moving wave and a backward moving wave. Sigma, we will be able to figure out that sigma is going to be a negative quantity, and as a result you are really going to get an attenuation over space. Okay. So, basically the intuition is like this: you get a forward moving wave, you get a backward moving wave. The net voltage is a sum of the forward and the backward moving wave attenuated in terms of distance because of the loss. Okay. So, we shall stop here and we will carry on from the next class. Thank you.